Hope all of you are well. Today I welcome all of you in my next video lecture. This video lecture we are going to discuss about the quasi-linear partial differential equation of the Lagrange's equation and how to solve this Lagrange's equation by direct integration method. Those things today we are going to discuss. So let us start our today's topic. So as I have told you, before we are going to discuss, we have to know what are the learning objectives of today's video lecture. So by the end of this session, we are thinking that the students or the learners will be able to identify the Lagrange's quasi-linear first order partial differential equation and solve it using direct method by forming and integrating its auxiliary equation. So let us try to understand what is the quasi-linear partial differential equation. So the basic difference between an ordinary differential equation and a partial differential equation is in the classification of their equation. Usually in case of an ordinary differential equation, it can be classified into two categories. One is linear, another one is non-linear. But in case of the partial differential equation, it can be categorized into four types. First of all, linear, semi-linear, quasi-linear and non-linear. So let us try to understand what are the classification and how to understand it from the equation structure. So if an equation given in the form capital P into small p plus capital Q into small q equals to capital R, where small p and small q are the standard notations. I think all of you now habituated with this if you have noticed the previous video lectures, where capital P and capital Q and capital R, these are the coefficients. This can be function of x, y, z. So depending on this x, y, z function, it can be categorized under linear, semi-linear, quasi-linear, non-linear category. So in case of the linear, this capital P and capital Q both must be function of independent variables only, that is x and y only. Capital R is also a function of x, y, z, but there is a restriction that R must be linear in z, that is inside of R, z square, z cube or higher order or any kind of order other than z to the power 1 cannot be present. So let us take some example to understand this linear equation. Suppose I am taking x into p plus y into q, this is equals to z. So this becomes a linear partial differential equation because the coefficient of small p containing function of x and y, coefficient of small q containing function of x and y, and the right hand side capital R where it contains z but z to the power only 1 is present here. Another example we can take, say x plus y into small p plus x square y into small q equals to x, y, z. So this is also a linear partial differential equation because the coefficient of small p containing x and y, coefficient of small q also containing x and y, right hand side capital R also containing x, y, z, but the z power is 1 here. So it comes under the category of linear partial differential equation. Now we are going to discuss about the semi-linear. Here we are going to give some relaxation in the z. So a equation or partial differential equation of the same structure, capital P into small p plus capital Q into small q equal to capital R, is said to be a semi-linear partial differential equation if capital P is a function of x and y only, capital Q is a function of x and y, but in R there is no restriction, it can be function of x, y, z, and also there is no restriction over z, that is power of z can be anything. So suppose if I take an example, say sine of x into small p plus sine of y into small q, this is equal to say sine of z. So what we can see here, coefficient of small p containing function of x and y, coefficient of small q containing function of x and y, where capital R is a function of z, but in case for linear it should not come, it should be linear in z, but here in semi-linear that restriction over z we have resolved. So that is why it comes under category of semi-linear equation. Next one is the quasi-linear and one of the most important and interesting type of partial differential equation. So an equation of the form capital P into small p plus capital Q into small q equals to capital R is said to be a quasi-linear if we can see there is no restriction on P, Q and R. That is, all this capital P, capital Q and capital R must be function of x, y, z. It can be function of x, y, z. So for example, say I am taking x plus y into small p plus y plus z into small q equals to x plus z. So what we can see here, that is coefficient of small p containing x and y only, coefficient of small q containing y and z. This type of thing we cannot do for the semi-linear or linear category. And here right hand side it is okay, function of x, y, z. So here this comes under the quasi-linear type of partial differential equation. Non-linear, that does not comes under any one of the three cases that already we have discussed. So in the previous two video lectures I have solved only the first order non-linear partial differential equation and their types. So if you still have not checked it, then please go and check all the videos for your more clarification regarding the non-linear partial differential equation. Before we are going to start the topic of solution of Lagrange's equation, let us make a note here. You have to remind one thing, that is those equation which are already linear, it can be treated as a semi-linear problem also, and semi-linear problem can be treated as a quasi-linear problem. Because in linear much more restriction is there, in semi-linear little bit less relaxation we have is there, and in quasi-linear we have relaxed more in terms of z. So every linear problem can be treated as a semi-linear, more or less it can be treated as a quasi-linear also. So if we know how to solve first order quasi-linear partial differential equation, then easily we can be able to solve the semi-linear and linear type of problem. But remember, the reverse order cannot be followed, that is every quasi-linear cannot be semi-linear and every semi-linear cannot be a linear type of partial differential equation. Now let us come to our description. So what is a Lagrange's equation? A first order partial differential equation which must be a quasi-linear type of equation of the form capital P small p plus capital Q small q equal to capital R. This particular structure actually it is known as a Lagrange's equation. Okay, so how to solve it? If you have checked my video lectures for the removing of arbitrary constant and removing of arbitrary function to create the partial differential equation, then you have remembered that while we have eliminating the arbitrary functions, we have received this type of equation, phi of u comma v equals to 0. This type of form was given to us. Our task is to remove this phi function, and ultimately we have removed this phi function and we have finalized the equation. So whenever we have got the equation, the structure of the equation basically in the Lagrange's type. If you have not checked it yet, you can check and you can understand that this structure after removing of phi function, the structure of the form will be of the Lagrange's equation, that is capital P into small p plus capital Q into small q equals to capital R. Now how to come to the solution technique for this type of problem? Let us try to understand. Suppose we consider u equal to c1 and v equal to c2. Say two differentiable functions, this u and v basically functions of x, y, z. So x, y, z equals to constant and another v equals to x, y, z equals to constant. two quantities we are considering, two differentiable carbs. Then by concept of total differential that we have learned from the functions of several variables, that is du can be written as del u del x dx plus del u del y dy plus del u del z dz. Now since u equal to c1, so differentiation of u, that is going to be 0. Similarly, differentiation of v, that is dv, it can be written as del v del x dx del v del y dy plus del v del z dz equals to 0. Now if I put this equation 1 and equation 2 and try to cross multiply, then we know that dx upon what will be the term, the coefficient will get cross multiplied, that is del u del y multiplied with del v del z, minus this 2 multiplication will be there, del u del z into del v del y. So this will be under dx. Similarly, dy upon, how we will get del u del z into del v del x. Whenever we are thinking of dy, then we have to just obsolete dy and we have to think from dz to dx and dx to dz. So del u del z into del v del x minus del u del x into del v del z. Similarly, dz, whenever we are thinking, then this dz terms we have to just eliminate and we have to multiply the coefficients of dx and dy. So del u del x into del v del y minus del u del y into del v del x. So these terms actually are nothing but the coefficients capital P, capital Q and capital R that is given in the Lagrange's equation. So basically it will become dx upon P, dy upon Q, dz upon R. So this equation we have to remember, and this equation is known as the Lagrange's auxiliary equation. Lagrange's auxiliary equation. Okay, so this capital P, capital Q, capital R, if you remember, this type of things we have already find out while we have removed the arbitrary function that I have made the video lecture 2. Okay, so now let us come to the today's topic, how to work with this type of equation. What are the working rule for this? Say the given equation in the structure of capital P small p plus capital Q small q equal to capital R. This will be our given structure. We have to identify capital P, capital Q and capital R. Thereafter we have to write down the auxiliary equation, that is dx upon P, dy upon Q, dz upon R. Now two terms we have to take and directly we have to integrate. Suppose anyone can take first and second factor. Integrating, you can obtain one family of curve, that is u equal to c1. Now you take any other two terms in such a way that integration can be done very easily, say first and third or second and third, so that you can have another family of curve, say v equal to c2. So what will be the general solution for this type of problem? That is going to be phi of uv equals to 0. So this is our target that we have to receive. Now let us come to the problem, how to understand and apply this technique. Say the first problem gives us small p into x plus small q into y equal to small z. So if we compare this structure with capital P into small p plus capital Q into small q equals to capital R, then what we can obtain from here? Capital P equals to small x, capital Q equal to small y and capital R equal to small z. Therefore, what is the auxiliary equation? Therefore, the auxiliary equation is dx upon capital P, that is equal to dy upon capital Q, that is equal to dz upon capital R, right? So this imply the equation becomes dx upon x, this is dy upon y, this is equals to dz upon z. So now you take two factors, any two factors I can take. Say I am taking dx upon x with dy upon y. Now I can simply integrate it. So if I simply integrate it, what I will get, that is log of x equals to log of y plus log of C1. This log C1 is coming due to the integrating constant. Now log Y, we can take it on the left hand side. Log A minus log B is log of A upon B. So we can write down log of X upon Y. This is equals to log C1. So we can exclude this log by taking exponential power. So x upon y equals to C1. This is our first family of curve or first solution. Now we are going to calculate the second family of curve. Let us take any other two factors. Say I am taking first and third. So dx upon x upon dz upon z. Similarly, by the same integration, what we will get, x upon z equals to C2. Therefore, we are having another family of curve. So say this is our u, this is our v. Therefore, what is the general solution? Therefore, the general solution is phi of x upon y, x upon z. This is equals to 0. So this is our general solution. Okay. Now let us come to the another problem to understand it. Solve y square z into by x into p plus xz into q equals to y square. So again, if we compare, what we will get from here, comparing, we have capital P equals to y square z upon x, capital Q equals to x into z, and capital R equals to y square, right? So it is a quasi-linear problem because coefficient of P contains xyz, coefficient of Q also contains xyz, but the previous question is a linear question. So now we can solve it by the auxiliary equation. Dx upon P equals to dy upon Q. This is equals to dz upon R, right? So this imply dx upon y square z upon x. This is equals to dy upon x into z. This is equals to dz upon y square. So now you take two factors. Say I am taking first factor and the second factor. Why I am taking? Because I can see that z can be cancelled out easily. So we can have x dx. Just I am taking this x in the reciprocal form. So x will go in with numerator, y square z. This is equals to dy upon xz, right? So zz can be cancelled out. So after cancelling zz, we can integrate it after taking this x with this x term. So we have integration of x square dx. This is equals to integration of y square dy, right? So after integration, what we have, x cube by 3. This is equals to y cube by 3 plus c1 by 3 I am taking. So x cube minus y cube equal to c1. So this is my first family of curve. Now which two factors we have to consider? If I take second and third, we don't have any common thing, so that we cannot cancel out, and x will still persist with this factor. So second and third will not give you the answer. But if I take first and third, then you can see this y square term will get cancelled out easily. So I am taking dx upon y square z upon x. This is equals to dz upon y square. So basically this y square get cancelled out. X dx, this will become z dz. Now you can integrate easily, okay, because it is separable of variables already. So it will come x square by 2 equals to z square by 2 plus c2 by 2 I am taking. So this imply x square minus z square equal to c2. So we are having the another family of curve. Therefore, what is our general solution? Therefore, the general solution is phi of x cube minus y cube x square minus z square, this is equals to 0. So this is the solution. Let us simply apply the same technique for the third problem. Solve small p into tan x plus small q into tan y equals to tan z. So here capital P is tan x, capital Q is tan y, capital R equals to tan z. So auxiliary equation is dx upon p, dy upon q, dz upon r. So I am taking these two factors together, dx upon tan x, dy by tan x, integration of tan x is log of sin x. So log of sin x equals to log of sin y plus log of c1 I am taking for removal of log. So we get sin x minus sin y equal to c1. Similarly, any two other factors you can take. I am taking first factor with the third factor. So dx upon tan x, dz by tan z, we have integrated and we got the answer as sin x by sin z equal to c2. So the general solution is phi of sin x by sin y, sin x by sin z equal to 0. So these are the things that we have to do during the direct method. So what are the things today we have learned? Basically we have learned the classification of the first order partial differential equation, that is its 4 types. Along with that, all of you have learned how to formulate and solve Lagrange's quasi-linear partial differential equation using the direct method. Some exercise questions I have given to you, simple problems. You try to solve it and please write a comment. If you are not getting the answer, then definitely I will help you. Thank you all.